Let's look at what happens when the normal force is acting as a centripetal force in one case. In this case, what happens on a banked turn. So if we're given a banked turn, and we'll have a go through a curve here, and we'll see that we'll have a car going around this turn. There's the wheels. There's the driver. It's moving away from us, going around in this direction like that. And if you recall, the normal force is perpendicular to a surface. So the normal force would be acting in this direction here. The acceleration on the vehicle is which way? It's directed towards the center. And so this would be the direction of the centripetal acceleration. Centripetal acceleration acts towards the center. We're going to set our axes so that the acceleration is along the x direction. Let me just make a further note that the car is moving at constant speed. Car is moving at constant speed. Not constant velocity because its direction is changing, but at constant speed. So we set our axes, so that a sub c is in the plus x direction. And let's see what happens if we do that. If we do that, I have y and x, and you can see this is my plus x. And let me just extend the page here a little bit. We have the car sitting on the incline. And we have the normal force going up like this, perpendicular to the surface. We have mg going straight down like that. So a sub c, the centripetal acceleration, is along the plus x, and mg is along the minus y direction. Unfortunately, f sub n must be broken up into components in the x and y direction. And as you can tell from this, let's do that. In the y direction, we're going to get, this is going to be f sub n in the y direction, and this is going to be f sub n in the x direction. And if you look at the diagram, you'll see that the angle, let's see if I can pick out a different color here. The angle here, right here, whoops, there we go. The angle right here, this angle, that angle is theta. That, it turns out, is the angle of the incline, which is right there. Very much similar to when we studied incline problems. Remember, this is looking back at this diagram up on the top. This is nothing more than an incline, and this angle of the incline is theta. It's a banked turn. And so that angle is the same as, that angle I've colored in there is the same as the other angle there. And you can show this using geometry, but we will we'll forego that proof right now, but those angles are the same, so that we have the following situation. We have, let's draw the triangle over here so we can see it a little bit clearer. We have f sub n, we have f sub n in the y direction, which you can see from up here is going to end up equaling mass times gravity. And you have f sub n in the x direction. This angle is theta. So from this you can see that the sine of theta is going to equal f sub n x over f sub n, or f sub n sine theta is going to equal f sub n x. Correspondingly, the cosine of theta is going to equal the adjacent, which is f sub n y, over the hypotenuse, f sub n, or f sub n cosine of theta is going to equal the y component. So now that we've got that done, we can do our analysis of the breakdown into terms of how do we determine a velocity around this turn. What is our velocity? How fast can we go around this turn, relying only on the normal force as the centripetal acceleration? So to do this, we set up our two equations. The sum of the forces in the x direction is going to equal m times a, again, sub c, the centripetal force, and the sum of the forces in the y direction, which in the vertical y direction, the car isn't moving. We don't want it being sliding up the ramp. We don't want it sliding down the ramp. We want it maintaining that position on the ramp, so there's not going to be any acceleration in that direction. And looking at our diagram here, we see that the only force, let's go back up here, this diagram right up here. We see that the only force, this was the direction of our centripetal acceleration here, the only force acting in that direction is the normal force in the x direction. So what I would write down here then is f sub n in the x direction equals m ac. Now, I know what f sub n in the x direction is. It's f sub n times the sine of the angle, which is equal to m times v squared all over r. So we're getting into the velocity. We've introduced the velocity. We want to get rid of the normal force. So let's solve the y direction. In the y direction, you can see from the diagram up here, okay, again, you can see that the weight, mg, is going to be equal to the normal force. The normal force would be located here. The mg, the weight, I should say, is there, and that's going to be equal to f sub ny. So when we write that out, we have f sub ny pointed upward, mg pointed downward. They should add up to 0. We know that f sub ny from above is f sub n times the cosine of theta. That's going to equal mg. And so f sub n equals mg divided by the cosine of theta. Well, now we can take this piece of information and plug it into here for f sub n. So if I do that, I get mg divided by the cosine of theta times the sine of theta equals mv squared over r. Once again, you can see one variable on both sides of the equation that we can get rid of, and that's the mass. Once again, we're independent of mass here. I get g times the sine of theta divided by the cosine of theta equals v squared over r. The sine over the cosine is a tangent. G tan theta equals v squared over r. And solving for v, we get v squared equals rg tangent theta, or v equals the square root of rg tangent of theta. Now this is with no friction. And so therefore, you can only make a turn at that velocity, at that particular velocity. And of course, you could solve for the radius, you could solve for any one of those variables, but that is what our goal was in this problem.